So I think, Wahid, it's time to hand over the microphone to Professor Kantarci to because the number is rising, and I believe it's going to be like okay right now. So.
Okay, can I start now?
Oh, yes, please.
Yes, please, Dr. Kantarci.
Well, first of all, let me start by thanking you for the invitation. It's a great privilege to be speaking to young professionals. I'd like to say it hasn't been so long time ago that I was in your shoes, but unfortunately years are flying, and it's been some time that I was considered within that window. And it's also a very nice organization because you have involved many chapters. I believe this is mainly led by IEEE Montreal chapter, but it is also followed by IEEE Turkey, Ottawa, and Vancouver chapters, if I'm not mistaken. So as I said, it's great to be talking to the young audience always. Because I believe curiosity is what drives the research, and that is the main motivator behind my research as well. Being curious and passionate about what I am doing, and that's what I always try to tell my students. I see one of my students on the call, so he can tell me later on or tell us later on if this is true or not. When I started working on this topic, AI-enabled wireless networks, it was almost 4 or 5 years ago. We started or we put the seeds of these kind of works when I was at Potsdam. Before I came to University of Ottawa, I was a professor at Clarkson University in the US, and we were working on smart grids, and we said, we need better communication networks, basically, so what can we do? And of course, machine learning was on the rise, and it is still on the rise at this time. And we thought maybe we could apply some machine learning techniques to improve smart grid communications. But then soon after, getting into that field, we realized that this is going to be an area where things are going to explode. It's going to be really interesting. There are so many research problems to solve and so many interesting things to look at. So at that point, we started looking into 6th generation of wireless communications, where we said, okay, we've been working on LTE for some time. We did some things in 5G, but then let's look at what's going to happen in 6G. So that's why the title of this talk is AI-enabled wireless networks, as I see it, as a bridge from 5G to 6G. And just to repeat Wahid's introduction, nice introduction about myself, my name is Melike Erol-Kantarci. I'm a Canada Research Chair in AI-enabled next-generation wireless networks, and also an associate professor at the University of Ottawa. I'm the Director of Network Systems and Communications Research Lab, and I'm also an IEEE ComSoc Distinguished Lecturer. So let's get started right on time. It hits 12 p.m. and we can get started with talking about what I'm going to introduce you today. And unlike maybe you were assuming that I was going to start talking about 5G and 6G first, I'd like to flip things over a little bit in my talks, and I want to start with the machine learning part. And the reason for that is, usually we are very fresh at the beginning of the presentation when we're listening to someone, but then, towards the end, it gets maybe a little bit boring and sort of routine, monotonous, and we tend to lose our interest. So let's get the math out of the way as soon as we can when our minds are fresh, and then continue with, some interesting works that I want to introduce today. So human intelligence, let's start with it. I mean, with AI and machine learning, what are we trying to do? We're trying to reach human intelligence, and even, animal intelligence is fine at this point, because human intelligence is very, very complicated. At the times when first AI research started, many of us and many of the AI researchers thought that expert systems was the way to go. Like if we gave the rules to a machine, the machine would follow the rules, and then we would be able to achieve some intelligence. But then people noticed that, as humans, we are not thinking that way. We are not born with the rules. We learn by interacting with the world. And it is no surprise in psychology, these trial and error kind of works, like remember Pavlov's work with the dogs, they have been tried. Like you give a treat after an animal performs what you want to do. The same with babies. I mean, nobody tells us some of the things that we should be or shouldn't be doing, but we experiment and then we get that experience. And if we like it, we do it. If we don't like it, we don't do it. So this type of particular type of learning is called reinforcement learning. In machine learning, for those of you who are familiar with the concept, there are supervised learning techniques, unsupervised learning techniques, and as a different branch of unsupervised learning, there is reinforcement learning. The two previous, supervised, unsupervised, usually works on data. So you have a pool of data, and then you apply machine learning techniques to it. In reinforcement learning, we don't have data. We interact with the environment. So for that reason, we create a realistic environment. We have agents. Agents interact with the environment. And then what happens is that there's a dog shaking his tail. The dog receives a reward. It's an agent, right? So the agent interacts. By the way, let me just put this into full screen so that I can use my cursor pointer, laser pointer, yes. So the agent interacts with the environment and then through making an action, and the state of the agent moves forward or changes, and as a return, the agent receives a reward. This reward is extremely important because this is how we teach our agents what to do. And in most of the problems, we have this situation, like we have many branches. Imagine a chess game. For those of you who are chess fans, I'm sure you know there's a lot of ways of winning and unfortunately losing a game. And one move of any piece on the board changes the entire situation of the game. So for that reason, after repeatedly playing or taking some actions by the agent is able to understand what brings itself better rewards. This bolded line that you see over here is a representation of an optimal policy. So among all possible branches, all possible ways that we can find, this has been a good one. So then the question is, how do we define good or bad mathematically, right? We need some numbers. So for that, we have to go to the roots of Markov decision processes, which actually came or converged with machine learning by the help of Richard Bellman in 1950s. He applied this to optimal control theory problems and was able to mathematically formulate and come up with the very famous Bellman equations that I will show a few slides later. But first things first, the definitions. ST shows the state of an agent at time t. AT is the action taken by the agent at time t. Now, the rewarding mechanism works as this. Given that an agent is at a certain state, ST, and it makes an action AT, the clock ticks and it receives a reward of RT plus 1, and the state changes to ST plus 1. Now, if you have a deterministic machine or if you have a deterministic system, what will happen is that each time you are in a certain state and do the same action, you're going to switch to the same next state, plus you're going to receive the same reward. However, in real life, things may not be as such. So we might have the next states as a probability. So with certain probability, we might go to one state. With certain probability, we might go to another state. And with certain probability, we may receive a certain amount of reward. We may receive another amount of reward with some other probability. And the agents will interact with the system, the environment in trials, in episodes, and at the end, it will find a policy. there is a policy and there is an optimal policy. Now, how do we define it? First of all, formally, policy is a mapping from states to actions. And the value of a policy is very important. That's a numeric value, and it's computed by the help of reward. So if you look at this equation over here, we are looking at the expected reward. This is an infinite horizon definition. For a finite horizon, we would be able to just adapt the rewards without any discount. But if this is an infinite horizon problem, we have to discount the value of the future rewards. Imagine you're playing chess. You don't want to reward yourself something that will give you a reward that will give you a good outcome 10 or 100 steps later. So you want to discount, and this gamma is between 0 and 1. That's how it discounts the value, is multiplied by the future rewards. And it's an expectation because of the stochastic nature of some problems. Now, there is another probability included in this, which is the state transition probability that we saw in the previous slides. If we have a deterministic system, this would be just crossed out, but for a stochastic system, we would need to include this into our equations. But what we have here is a symbol, this is a Bellman equation, a simple representation of the optimal reward, where we are trying to calculate find the actions that will give us the maximum reward, which can be done by looking at iteratively at the future rewards. So if we have all these probabilities, all this information, actually it is easy. We can just write a dynamic program and compute the results. But in real life, of course, things are not that easy because we are mostly working with model-free environments. And wireless is a model-free environment, and there are lots of things that are stochastic that comes into the play, like the channel models, user behavior, traffic behavior, mobility. All that is contributing to the stochastic nature of the environment. So for that reason, we use something very useful that's called temporal difference equations, which was developed around 89 by Richard Watkins. And what he came up with was to find a way of making an assignment to the Q values or the value function that we saw before. And the way that we do it is through, again, we have a discount value, that gamma that you saw in the previous slide is here. So discounted value of the future rewards with the difference of the current reward. And we have a learning rate here. So we want to adjust how forward we can jump in how much forward we can jump in our learning. If we jump too much ahead, then we may miss some of the opportunities that could happen in the middle steps, or if we go with too little steps, then our convergence time would be too slow. So after this capability of using temporal difference equations in model-free environments, we need one more capability, which comes where the exploration and exploitation in reinforcement learning comes to help at this point. So because the style of learning is sort of by trying out things, we need to try out sometimes risky actions as well. Because as we know from many optimization problems, sometimes we can get stuck at one point and we can't reach the global optimal solution that we are looking for. So to avoid this, we have exploration phase in reinforcement learning. But we can't explore forever, so we have to exploit what we have explored in some phases too. So that's why machine learning people have investigated this, and they have come up with an epsilon greedy approach, which selects an epsilon value, which is a small value that helps us take some risky actions. And if that risky action leads to a better reward, then that's fine. We have found our way out of the local optimal solution. We can continue. Or if we are good with it, if that was a risky action, that will not impact too much our future rewards, because with a large epsilon, we would still take non-risky actions. So most of the times, our agents would be taking non-risky actions, but a small portion of time, they would be taking some risks to improve the value of the reward and the value of the policy. Now, this is fine, but this type of learning that I'm talking about requires, especially the temporal difference equation, requires all Q values to be stored to be able to do those computations. These are called tabular reinforcement learning methods. Now, I'm taking you towards the deep reinforcement learning because reinforcement learning and deep reinforcement learning techniques are the techniques that we use most in our studies in my lab. So Q-learning is nice. As I said, it provides us a lot of interactive capabilities, learning opportunities, but because we need to store all these values. So if you have large state and action space, that's a problem. Plus, if you have a continuous state space, that's another problem. So to avoid this, what can we do? So imagine, I'm talking about basically a matrix of some values. Imagine I asked you to find a simple way to represent those values. What would you do? It's just like an estimation problem over some data. Of course, the basic way to do it is least mean squares method. You just draw a regression line and then find the two parameters that belongs to this line. If you want to complicate your model a little bit, you can try to draw a curve. The polynomial complexity, you can choose it depending on the cost of the system. So that's basically putting a filter for your data. And good news for that, neural networks works as a very well, like a filter themselves. So what we can do is place a neural network as a function approximator of the big bulky Q table that we don't want to store and drive the reinforcement learning with that. Now, for those of you who are not familiar with neural networks, a very, very brief introduction, super brief introduction. First of all, the roots of neural networks goes back to 1950s, 60s with the idea of perceptrons that were developed by Frank Rosenblatt. So the basic thing that happens here is that we have the inputs that comes into a decision circuit. And we want to guess or find out the weights of this inputs so that we will have a desired output. As you see over here, if the weighted sum of the inputs is below a threshold, we would have the output 0. If the weighted sum of the inputs is above a certain threshold, then we would have the output as 1. Now, this type of threshold function is very limiting, of course. We usually use sigmoids or arctangent functions to drive the neural networks. But the idea is the same, because what we are trying to do is we're trying to find the weights of how much those input values will impact the output. And this is just a single perceptron, the father of neurons, let's say, in neural networks. If we put these neurons one after other, and if we organize them in layers, we achieve or we get neural networks. And what we try to do in neural networks, or the problem is what? Is we have some inputs, we have some output or outputs. We want to classify the input to certain classes at the output. And to be able to do proper classification, we have to find out the weights that helps us understand how much of which input would contribute to the output. If we have an input layer, an output layer only, that would be a shallow neural network. If we have more hidden layers, then that would be a deep neural network. Deep neural networks have found use in many, many places. Of course, computer vision, NLP, are like the fortress of these techniques where they developed and they got really, really advanced. Convolutional neural networks usually useful for computer vision problems, and recurrent neural networks are useful for NLP problems and many others. Especially whenever we have a problem where history is important, just like networks, no surprises, we can resort to some type of RNN. And RNN is actually interesting. I mean, I like it very much because maybe some of you have heard of this AI winter concept that was in the history of AI. So there was big funding during Cold World War to process texts coming from certain countries by US. And so they were investing a lot in research to find out what the messages were without human translator involvement. And the translations didn't come out very well because of the methods used were not really efficient. But the beginning of 2000s, RNN was discovered, or that was tried, and it showed great success in NLP. And the secret sauce of RNN is that it can capture the temporal dynamic behavior by this feedback loop, or any kind of feedback loop that we can create. Different architectures are possible, of course. And it will allow us to basically remember what has happened several steps, or maybe even hundreds, thousands steps before. A special type of RNN is an LSTM, which we use a lot in our research as well. As for LSTM, there are two inputs to the LSTM unit. The first input is the memory of the previous unit. So that's how we carry the memory from one neuron to the other. And of course, as usual, we have the output of the previous unit that's coming to the current unit. So these inputs pass through forget and input gates, and they are translated and given to the next unit that's following the layer of neurons. So when we look at this, LSTM becomes a very useful tool for networks as well. And if you combine it, what I said before, so we want to avoid from, but first of all, we want to have interactive learning, because there are situations in networks that we don't have the data. So we want to create an environment. We want to have our agents interact. So reinforcement learning might be a useful tool. But because of the tabular Q-learning problem, because we need to store so many values, we may resort to neural networks. Then research has evolved saying that, okay, maybe we can use LSTM. And the innovation did not come from actually a computer networking perspective. As you might guess, it came from gaming perspective, because games like chess playing machines, AlphaGo machines, all those are actually driving the research in RL and DRL a lot. And this is something, this architecture of deep reinforcement learning that I'm showing here, that was first proposed in 2015 by DeepMind researchers in their paper in Nature, Human Level Control through Deep Reinforcement Learning. So what's special with this architecture is that it has all the things that I described before: reinforcement learning, LSTM, but it has several things more, like having a target deep neural network and an actual deep neural network, where the trained copy of the neural network is updated, like behind the scenes, so that we don't get into the problem of instability. And another thing is having the experience replay memory, where the batches of past experiences are stored and are used to drive the networks. And drive the reinforcement learning, sorry. And as you see here, this is like inside the G-Node-B, so we're getting close to the wireless concepts. Don't worry about it. G-Node-B stands for new generation base stations of 5G, so it's an evolution from eNode-B. And as we can see, the way that we model in our research, which I will explain in a few minutes, is that we consider G-Node-B as an agent that is sometimes running Q-learning, depending on our problem, or sometimes running deep reinforcement learning algorithms, and it's interacting with the environment. Here, the environment is the wireless environment, full with its, fading attenuation, statistical channel properties, mobile users, traffic, everything that happens in here. And there's a feedback coming from the G node B, and we usually try to assume like what is available with the standards. So in most of the cases, that's the CQI, channel quality index, that we get. And action is, whatever problem that we are trying to solve. In the next part of the talk, like right after I talk a bit about 5G and 6G, I will show you some of our example works where we do resource allocation. So if the problem is resource allocation, then we decide on which resource blocks, physical resource blocks, to give to which users. So that becomes our action. Now, we have done the brief introduction of machine learning techniques that will be useful for the rest of the talk for today. Now, let's switch gears a little bit and talk about that famous 5G and 6G concepts. First of all, an old picture from 5G. I like using it because it gives us the perspective from the very beginning of 5G, but I mean, it was drawn some years ago, even probably more than 10 years ago. And at the time, when we were initially talking about what would 5G be, 3 service types emerged. And you can see all of these 3 types of services at the corners of this triangle. So enhanced mobile broadband, massive machine type communications, and ultra reliable and low latency communications. Now, we started with this vision, of course, but soon after we realized that, the researchers realized that having ultra reliability and low latency, especially, we're talking about 1 millisecond latency, which is still not achieved and very hard to achieve, and then 7 nines of reliability at the same time are very hard. They have contradicting requirements and settings in the network, so it's more like a square. Actually, it should be more like a square. But anyhow, this picture shows the use cases very well, so I want to talk about it for a few minutes. And something I like to mention, usually in my talks, is that the first generation of mobile phones started with what? We didn't want to talk from home. We wanted to have something other than a landline phone, and I don't know who has a landline phone at home these days, but so the whole story started with that. We wanted to be able to make phone calls when we were just outdoors, and this is over here now, voice calls. It's just a little dot in the map. So wireless mobile networks became huge over generation by generation. For 5G, the latest generation that is being developed worldwide, in most of the countries, there is one or other way of, maybe, in urban cities, a few 5G base stations these days. What we can do with 5G is that we can, upload, download those 3-dimensional videos from our social networking circles. Of course, we can connect to online meetings during COVID when we are outdoors. Of course, when we are home, it's usually Wi-Fi, but outdoors, 5G would be used. Augmented reality, virtual reality, extended reality, all those applications, like imagine you're playing a Pokemon style game with your goggles outdoors and you have other people doing the same. So that would be a typical entertainment service or entertainment use case for 5G. And then mission critical applications, industry automation like smart factories, even self-driving cars. Of course, they don't have to communicate for everything that they do. There's radar, LiDAR on the cars that usually helps with driving, but some safety messages tend to be over wireless networks, and 5G could be a potential place for that. And those are driving the ultra reliability use cases, because we want really very tight reliability, around 7 nines. We want close to 1 millisecond latency for certain applications like smart industry or smart factory applications where manufacturing process is fast and processing some items. And then on the very other corner of this triangle, we have massive machine type communications where everything is getting connected. The vision of IoT, this has been a story for many years. You must have heard it in many places like 4 billion devices, trillion of devices. So the estimations are growing each day. Of course, I mean, you don't have to connect all these devices over 5G, but 5G sees it like an opportunity as a market to jump in. Smart homes, smart grids, all of them are expected to be a part of 5G or can be a part of 5G. Now, the question might be, okay, we're talking about 5G and, you know, in some of the countries, we don't even see those 5G implementations or they're very rare. Why are we talking about 6G? Because, you know, right after this, I'm going to talk about 6G. It's because every generation of, I mean, in mobile networks, I would say, in every 10 years, we talk about a new generation. And the studies usually start 10 years or even further before. So if you don't talk about 6G right now, 10 years later, we won't have 6G. That's why. And going back to 5G, what makes 5G special, different than LTE? Why do we need a new generation? That might be another question. Is that usually every generation comes with a different PHY technology, a physical layer technology, and millimeter wave and massive MIMO are the sort of benchmark technologies or trademark technologies that are for 5G new radio. Millimeter wave ranges or frequency ranges spectrum is very broad. When it comes to commercial 5G deployments, we are not using all of these ranges. Usually in countries, it differs from one country to the other because their regulators decide which frequency, which spectrum to allocate. But it's around 24 to 40 gigahertz, although the actual millimeter wave goes much higher than that. And then there's the 6 sub-G spectrum, where we have low band and mid band inside, where low band is already used, but mid band is coming as a new spectrum allocation, where, you know, some of the existing allocations are taken from satellites, radars, and given to mobile operators in some countries. Now, these are the new spectrum. So having spectrum is wonderful. I mean, anyone who knows Shannon theorem knows that spectrum directly impacts the capacity, so that's a good thing. Now, the other thing that came as a part of 5G new radio and that makes 5G special is that both scalable slot duration and scalable numerology. Scalable numerology, first of all, is what? In LTE, well, it is about OFDM, first of all. In OFDM, subcarriers have spacing of 15 kilohertz for LTE. And these subcarriers are spaced such that their peaks are not corresponding with the dips of the other subcarriers. So they are orthogonal so that we can send substreams on each separate channel. This makes, you know, OFDM a very strong technology that is used in Wi-Fi and LTE. Now, 5G still we are using OFDM, but this time we have some flexibility because we can go up to higher spectrum. Now we can open up the bands a little bit, so we can have 30, 60, or 120 kilohertz, 120 kilohertz subcarrier spacing between the subcarriers of OFDM. And in addition to that, so this is the frequency domain of OFDM at the time domain. We have the flexible slot durations. 2, we can use it for mini slots like uRLLC, ultra reliable and low latency communication type, or we can have 14 OFDM symbols, which can be considered like jumbo time frames, and that can be used for eMBB, Enhanced Mobile Broadband traffic. Now, about 6G, so it's coming sound and strong. We are doing the research at this time. And of course, I mean, we need some PHY technologies to drive this, technology. And terahertz is actually emerging. But of course, I mean, before you ask, I should maybe point out this. First of all, we are not doing perfect with millimeter wave. We are at the lower range of the spectrum. So going to terahertz is super challenging, actually. Most of the time, the realistic assumptions come from considering terahertz for sensing or navigation rather than communications. But still, never say never. It might be possible to use some very short-range communications as well. A multiple access technique that has been actually developed and considered for 5G, that has been developed since some time, NOMA, non-orthogonal multiple access, where we use the same PRBs, physical resource blocks for the users, but we change the power, which, as you might imagine, is not an easy technique, because at the receiver, they're going to receive from same PRBs, but with different power levels. So they have to have really strong interference cancellation techniques. But anyhow, it might be possible. So it is still like a proposal that is being considered for 6G. Unlicensed spectrum, of course, it is not new to 6G. It has been considered in LTE, it has been considered in 5G, and it will be considered in 6G because spectrum is gold. It's very important. We need more spectrum. So if we can jump into any spectrum, let it be ISM band, let it be, you know, by cognitive techniques, the radar and TV white space, whatever, that we would like to do, of course. We'd like to make the best out of the spectrum. And then another topic that's very, very hot that is being studied a lot is the aerial networks, the drones. So these are very exciting topics as well. Visible light communications, this has been studied, researched for a while. And all of this, including intelligent metasurfaces as a new technique to improve physical propagation of the signals, are important, will be important parts of 6G. And we'll see, you know, who survives. At this point, it's hard to say what will get into the standardization, but there is research going all around these, you know, ends. And in the end, we'll see what defines the 3G standards. Aside from all of these, of course, there's a topic that I love, which is AI-based network automation, or AI-based wireless networks, or network automation. A lot of names for it, but a lot of the people from academia and industry accept that this will be a fundamental technology for 6G. We will definitely have it in 6G. And why is this important? And maybe even before that, is this new? Okay, because whenever you talk about something in wireless, people say, oh, we've heard of it before, you know, we already have it. Sometimes that's true. We already have some sort of automation in wireless networks. And 3GPP, from the time of LTE with SON, self-organized networks, actually had the initial seeds of this automation. But the automation at that level is basically the ability to put base stations in the field and be able to configure their PCIs or some basic configuration values without sending engineers to the field. Of course, this is nice. This helps easy deployment of base stations, but it is not enough for 5G and 6G. And the reason is that the complexity is growing. Like we talked about millimeter wave, but I didn't tell you one thing. When we use millimeter wave, the challenge here is that the propagation loss is huge. So millimeter wave signals do not travel very far away. Because they do not travel very far away, we use beamforming techniques to increase the range, to focus power in a certain direction. But that creates what? That creates small and directional cells. So imagine, I mean, previously in LTE, we were talking about the base station that could cover 3 sectors with just one deployment. Now we're going to have little beams all around, and we'll have to look for their how to configure them, how to you know, set the power, how to have user cell association or user beam association for them. So all of them comes as new problems. Massive number of devices. This is from the you know, one of the use cases that we talked about before. Massive antenna arrays, massive MIMO, so requires a lot of parameter tuning for the antennas. MEC, multi-access edge computing. So no longer we can say, okay, we have the, you know, old-fashioned radio with a full hardware implementation, baseband right attached to it. Most of the times we are looking at deployments, and this is in connection to vRAN and ORAN, of course. We are looking at a supporting computing infrastructure. And with vRAN, we are able to rip off these network functions and implement them independent of the hardware on the servers. And with ORAN, we are getting the ability or implementing open interfaces. So interface details are usually written by the vendors like Ericsson, Huawei, Nokia, and several ZTE and several others, where some of the things are different than the standards. They have become proprietary over time. So what ORAN is trying to do is to have open up these interfaces so that multiple vendors come in and take part in the old monolithic base station would become disaggregated, and they would take part in some of, they would be players in some part of the RAN. And network slicing is, of course, a huge topic that also requires automation. And when we say automation, what do we mean? Before maybe discussing all of these, we mean that we are trying to minimize the human intervention. So how it happens in the operator's end is that for managing a wireless network, when there are faults or when there are some new configuration, there are engineers who are experienced with the system. They take some decisions. They first of all translate policies just to do the regular running of the regular operation of the networks, and then when faults occur, they pay special attention and try to find out what happens. So the aim is that with network automation to minimize that impact and do everything with the help of AI. Of course, I mean, this is a nice view. This is, this is something that's desirable, but at the same time, I mean, I have to tell you, this is not, this is still an active research area. We cannot say, I mean, all the things that I'm going to present here, we still cannot say, okay, take this algorithm, put it in the field, and it will work. AI algorithms are not ready for prime time. And at the end of the talk, I will explain you what are the challenges and what are the reasons for that. And let me check my time. Yeah, I believe I still have some more time. So I'm going to speed up a little bit after this talk because I want to introduce you a couple of works and I want to show you how we merge the things that we talked in the first part of this talk about reinforcement learning, deep reinforcement learning, along with the wireless concept. So one of the problems that we have been looking at is resource block allocation. Resource block allocation is a problem of OFDM. We have the frequency resources, we have the time resources, as you see over here, that can be organized or visualized like a grid. So when you try to, for example, upload or download a video, your base station, the one that your phone gets associated with, would give you some resources. So let's say you're going to get these resources. According to what the base station will give you, will take these decisions every TTI according to your request plus the channel quality. So the user, which is a metric for SINR, the user would measure, or our phones would measure the SINR value, convert it, map it to CQI values, would send to the base station would look at it, would look at all the users, find the channels that would perform well for you, distributed among its users, and then based on what quality channel you get, you would have a modulation scheme that would help you send your data. This is how things work regularly, of course. Now that with 5G, what do we have extra on top of that? We have two different traffic types, uRLLC and eMBB. These are competing traffic types because uRLLC wants to grab those resources, like it wants to get the first resource that it can from here, but maybe that channel belongs to eMBB because eMBB is a high throughput user. It needs to get a lot of subcarriers for a long amount of time. So it might be like dominating a big chunk of the resource blocks. So what to do with that, right? So for that, we developed a reinforcement learning or Q-learning based algorithm. Our aim, our action is to allocate the resource blocks in such a way that we maximize the throughput plus we maintain a certain latency. To model this problem, we have to, so this is the action of the problem, we have to model the states and the reward function as well. So for states, because this is a problem that is using Q-learning, we wanted to have a very simple state so that we don't get into the problem that I mentioned to you before about the tabular Q-learning methods. So we said we will have a desired CQI value. So if the CQI, if the SINR value, which is actually, directly related to CQI, SINR is a mapping to CQI. Anyways, if SINR is above a certain threshold, that means we are in the desired state. If not, we are not in the desired state. So the users, the UEs, will try to get the best channels as they can. With the reward, what we do is that among these good channels that have good SINR values, we want to limit the latency because we have uRLLC users as well. So the maximum waiting time in the queue should be less than 1. And if that exceeds, if the SINR threshold is not met, then the user is given a penalty. So the next thing that we did was to benchmark this idea, this proposal, with a technique that does not use machine learning. So a few months before our work was presented, there was another work that was published by Nokia researchers, and they proposed a priority-based proportional fare. Proportional fare is a well-known algorithm for resource allocation in wireless, and they proposed to have uRLLC with some priority, where uRLLC would puncture the resources from eMBB. So under low loads, we show that we have comparable performance, and under high loads, we show that our performance in terms of latency of uRLLC loads were actually superior. And we were able to do it by maintaining a same or better throughput and an improved loss rate in terms of the number of packets. So we were able to show that, a Q-learning mechanism can perform better than a proportional priority-based proportional algorithm, proportional fare algorithm. The next thing that attracted our curiosity was to figure out how we could apply this to a cell that is doing beamforming. Because we said, 5G, one of the benchmark technologies of 5G is millimeter wave. Millimeter wave, as a result of millimeter wave, we have directional antennas or beams targeted towards a certain user. So imagine we have these users in the middle. They are going to struggle with two problems. First of all, user-cell association, whether they're going to get associated to this cell, to this beam, or are they going to get associated to this beam? And what would be the power levels of each beam so that they would not create interference, excessive interference for each other? Plus, after the users are associated with the base stations, how would we do the resource allocation? So we tried to solve this problem, and we again used Q-learning for this problem. Actually, I'm not going to get into the details of this work, but because of time constraints. But I will explain you one thing that will help me talk about our the next thing that I want to mention before I run out of time. So whenever we use machine learning techniques, convergence is very critical because it is well known that reinforcement learning type techniques, and you can understand it from the definitions that I made, agent has to interact for a certain amount of time. Usually what we assume is that the base stations train themselves offline. So there are like two stages, an offline trainer and an online base station that is actually taking the decisions on the field. But whatever way these are implemented, again, shorter convergence time is desired. Like if you look at this technique, the one that we proposed for beam management in millimeter wave, after 2,500 TTIs, we can converge. So this is a large number. We wanted to find out a way to reduce it. So I will just, the performance KPIs were better than the other compared techniques, but I will not get into the details of that. I will skip this work as well that we presented in Globecom, and I will talk about a very interesting work that we did on transfer reinforcement learning. So one way to improve convergence could be to use using bootstrapping techniques like initializing Q tables to some values. But another nice way that we figured out was using transfer learning. So transfer learning is not new. Transfer learning has been used in the literature of machine learning in many times, many ways. But usually the way they are used is associated with data. So you have one data available. You learn one task from that data. In traditional learning, you would learn, if you have another data set, you would learn independently your second task. But transfer learning tells us that it might be possible to transfer the knowledge from previous data sources. Now, this is when you have the data. How do you do transfer reinforcement learning? That's a little bit different. You have to find mappings between expert tasks and learning tasks. So this is a very recently published article. Actually, I put here as accepted, but yesterday I think I got the volume and issue numbers. Over here, actually, what we did in that work is we trained our experts to learn user cell association by doing Q-learning. And then for the learners are millimeter wave, they're using millimeter wave, so they have to learn number of things, not just user cell association. So they are doing user cell association and they are selecting the number of beams. So to be able to do that, they are benefiting from the experience of the expert. And we showed that we are able to, so this is the convergence of the expert, but we need to look here. We can improve the convergence of the learner both by in terms of getting better rewards and also converging at a shorter amount of time by using transfer reinforcement learning is possible. But still those times are large, so we still have a lot of works to do to improve the convergence times or find machine learning techniques that can transfer base stations offline, that can train base stations offline and then adapt these learned actions to the actions on the field. So this is showing the KPI values that are performing better than the several baselines that we tried, both machine learning based algorithms and baseline algorithms that use basically or simple clustering techniques. So I'm going to wrap up my talk after this point and try to finish just in a couple of minutes. Sorry, I've been a little bit over time, but these topics always get me so excited that, somebody has to stop me. So why we see AI is going to be be in a spring season for when we talk about networks or wireless communications. There are certain things that makes us hopeful about this. The first one is that wireless networks and networks in general, with the help of SDN, they are becoming to be software centric. The other thing that is happening, has been happening since some time and still happening, is the ability to increase the number of computation at the edge, bring the computation closer to the users, and also disaggregation of the front haul. So all of these things are making networks more complex and bringing us opportunities for using AI. That's why I like to call it AI spring. Not AI summer, because we haven't figured out all the details yet. These are not ready for prime time, but there is a lot of promise in these techniques. Nevertheless, I don't want to print a pink picture for everyone, so there are challenges, of course. Convergence is number one that we are also working on heavily, that we want to have techniques that have shorter convergence time than the usual ones. Scalability is an important open problem challenge. Lack of standardized training sets. A lot of people in machine learning literature, academics in this area, know very well that the development of training sets, both in computer vision and NLP, has been very useful in developing the field. The same for wireless. There are here and there some data sets available, but we should have more. Well, most of the techniques that I talked today are single individual agents. But when we have distributed multi-agent systems, problems even grow, and we have to come up with interesting solutions. And finally, in networks, we are faced with rare events like faults, unreliability issues that happen once in a while, but when they happen, they really impact the performance negatively. So how can we learn from fewer samples is a very important problem for the future. So with this, I'd like to thank the students in my lab, and they are behind this great research, as well as the funding agencies that fund our research. And I'm always looking for new postdocs, new PhD students. They can send me an email if they are interested. So hopefully I have some time for questions. Shall I look at the chat, or would you like to?
You are muted, Vahid, you are muted.
Oh, okay, sorry. Thank you, Dr. Kantarci, for the very interesting presentation and very informative one. Actually, yep, we have a couple of questions here in the chat. The question says that how can we study about the high frequency wave radiation for engineering research? Common negative opinion to the 5G broadband is radiation hazardous to our health. What Dr. Kantarci think about this problem?
Well, that's a good question, although it is not, too much related with the AI-enabled wireless networks. My opinion on this in general is that in every generation, we come up with similar concerns coming from several circles. Sometimes they are founded, they have good ground, sometimes not. And I have to say, I mean, there are regulations in every country that looks into the radiation of 5G, and there are certain set standards. And usually operators follow this when they place a base station. So certain heights of the antenna, certain power levels, so that this radiation would not cause any impact on human health. And those values are usually set very, very conservatively. And in most of the cases, those antennas are not allowed to be placed in close proximity to schools, nurseries, and places like that. However, I'm a strong believer that anything that we support or say has to be supported by research. So governments and the network operators should be always, doing their duty, doing their assignment to test these radiation values, both when they are setting the regulations, and also when these antennas are live in operation. So active measurements has to be done all around these antennas all the time.
Thank you, Dr. Kantarci. So back into your reinforcement learning, I just have a very quick question. So imagine that you are accumulating and aggregating rewards for a learning or estimating channel. So you spend some time, you accumulated some rewards, and you are happy that okay, you are approaching the CQI, the CQI that you are looking for, or the modulation that you are interested for. So once up, suddenly a bus blocks your ray tracing, and everything just vanished. So everything that you have learned, so reinforcement learning needs to restart. So I think this is one of those drawbacks of the reinforcement learning and learning channels, and the high fluctuations, fadings. So especially in fast fading situations as well. So what is your suggestion or solution for this?
Very good question, and the answer is not easy. This is something that we know as concept drift in learning. So when the environment changes, becomes non-stationary, learning becomes problematic. So there might be many ways of avoiding this problem, and I would say this is an open research research topic. So one may consider fewer shot learning techniques that would help learning faster in such situations. And it comes back to what I said about learning the rare events. So we want to learn those very rare events and be able to act fast to those. Or there might be some backup mechanisms because, the idea is until AI techniques become mainstream and they can be put on the base station immediately, the trainer base station can take off some of the actions. So basically 2 modules in base stations, 1 trainer, 1 taking the action. The trainer may get the learning process ready for such unexpected events. But definitely that's an open problem. Those kind of non-stationarities can happen from even, some users coming in a bunch and just demanding some service that you did not anticipate for. These things can happen.
Thank you for your explanation. So I might have like a time for very one more quick question. So okay, I prefer to ask from our one of audiences. So I'm gonna drop my own question. It's gonna be like what are your thoughts on cell-free massive MIMO? Will it be an emerging technology for 6G, especially with the presence of reconfigurable intelligent surfaces?
Yes, this is one thing actually I did not mention, and it's good that it came up. Yes, it is coming as a sound and strong technology for 6G, cell-free massive MIMO. And yeah, we are seeing a lot of changes in the structure of wireless networks, and this is one of them. And I do believe, there are some works on reinforcement learning based configuration of RIS. And I'm sure, cell-free massive MIMO is another area where we can have a lot of innovations. And by the way, in this talk, I focused mainly on resource allocation, but there is a big bulk of works on higher layers that do AI for network slicing, plus another big bulk of works that are using ML, machine learning, or AI for physical layers. So like tuning massive MIMO parameters, doing DSP by using machine learning. These are very popular topics as well.
Thank you for your explanation. So back into slicing, I might have one more quick question. So slicing on RAN, so it recognized to be one of the most challenging problems in the resource allocation schemes. So given the fact that you are going to allocate resources or frequency elements in a very short and limited time, so let's say you're going to make a decision below 1 millisecond, especially for uRLLC systems. So I wonder, still reinforcement learning could be a key player to address those problems. So yeah, deep reinforcement learning has been shown that it converges many times. But like I said, if you see a bus that blocks the ray tracing, you lost everything.
But I have to say, this is not just a problem of reinforcement learning. It's very hard to find an optimal solution for RAN slicing. There are certain research works around optimization, which assume you got all the inputs. So usually we do some assumptions and we hope that they would work. And machine learning is actually used, reinforcement learning, deep reinforcement learning. There are studies who are using these for RAN slicing. The question could be, are they, satisfactory, or can we apply them? But then one can also ask, there are so many optimization solutions, are they satisfactory? So there's always this, finding the optimal problem. And when it comes to field operations, it's usually adaptive algorithms that are chosen, like an operator, knows what parameters they want to tune, and then they select it and they do it. So I see the techniques that we are developing will be probably assistive technologies at the first stage until they come to certain maturity.
Thank you, Professor Kantarci, for your inspiring presentation and your thorough explanations on the questions. So I'm going to hand over the microphone to Vahid to quickly introduce our next speaker. So hopefully start very soon. Thank you.
Thank you very much for inviting me. Thanks.
Thank you so much, Professor Kantarci. And Professor Karimipur, you may start, and you can introduce your lab and the type of research you are doing as you wish to, and can precisely introduce yourself if you wish. Thank you so much. And so we are.
Sure. So do you have the right screen, I assume?
Yes, we do.
Okay, perfect. Hello again, everyone, and welcome to my presentation. I'm Hazardous Karimipur. I'm one of the faculty member in University of Guelph, and my main area of the research focus on the security of the IoT and OT technology with the focus on different critical infrastructure, including smart grid. I did my PhD in University of Alberta, and then in 2016 I graduated from University of Alberta, and then I did a short-term postdoc in University of Calgary, and on July 2017 I joined University of Guelph. Today I wanted to talk mainly about intelligent cybersecurity analysis in IoT-enabled smart grid. So let's start with some background about the traditional power system. If we go back to 1882, when the Thomas Edison basically opened America's first power plant at Pearl Street Station in Lower Manhattan, his goal was to deliver the power to almost 59 customers. And since then, the customer base, the overall architecture of the basically power system, transportation, electricity generation, and everything is kind of the same, but the number of customers is increasing to thousands and 10,000 and millions of basically customers. But the overall architecture, as I said, is the same. So in another word, the traditional power electricity grid, which was developed basically many years ago, was a centralized basically system with very limited automation and no user interaction. That was the system that was enough to deliver power to limited basically customer. But nowadays, due to the increase in the number of customers and the huge electricity consumption, the traditional grids are under high pressure to deliver the growing demand for powers, as well as providing a stable and reliable supply of electricity. Besides that, most of today's generation capacity relies on fossil fuel, which basically increase the carbon dioxide emission in the world atmosphere and change the climate and the society in general. And on top of everything else, the traditional power system it was not designed basically to incorporate the power generation and storage at the distribution level. With a traditional system, we cannot use distributed generation, wind power, solar cell, or other type of basically renewable energy sources. So because of all these changes, we need to change the existing power grid and shift toward a more basically advanced sort of technology to be able to satisfy the growing demand. And a smart grid is basically the enabler for this transition, which helps us to move to the new technology. The concept of a smart grid basically incorporates a networks of generation, transmission, and distribution component that undertake power delivery from bulk generation power plant and distributed generation to various type of load. So the components are governed and managed by intelligent devices from generation to consumption. Generally, a smart grid allows utility to engage customers in power generation and may implement a bi-directional power exchange, basically, between customers and the utility centers. So if I wanted to define a smart grid, I would say much in a way that a smartphone is a phone with computer in it, I can say a smart grid is a computerized power grid. And it comes with lots of basically different components. It has lots of information-based components. It has communication network attached to it. It should be a self-healing basically system because lots of components are in the distributed location, in the isolated location. And it should be a more reliable and flexible basically source of energy production. And because of all these basically attributes of the smart grid, it's generally more cost effective and it's easier to control it in somehow. It has its own challenges, but compared to the traditional power system, it's easier to automate and control the systems. So it has lots of basically advantages, but at the same time, it also has its own technical challenges. To be able to take advantage of this smart technology to make the basically technology smart, we need huge amount of data exchange between the grid component and the enterprise system that manage these components. So for a smart grid, data exchange is essential for controlling, monitoring, and coordination between the smart equipment and the subsystem. Another important, basically, challenge in the smart grid technology is the communication network that we have to basically add into different layers of the system. We have to change a traditional system which was designed in a different way, and we have to connect it with lots of communication network. We have to allow different components to communicate with each other. And another basically challenges, let's say, that we have to address is related to the cyber component of the system, because we have lots of information and communication technology that basically will support the integration of the intelligent and collaborative system. But at the same time, because they are new to this system, they might make the whole system vulnerable to different type of threats like security threats. So before we can take advantages of the smart grid technology and we can implement it fully, we have to answer some sort of questions like that, how we can basically take advantages of all the data that we are generating all over the grid in an efficient way to basically monitor the performance of the system, how we can ensure that the system is secure and we can control different basically aspects of the system, how we can ensure that the communication network is basically safe and secure. Otherwise, if we basically ignore all these questions and all these challenges, we might cause lots of problems and we might not be able to take full advantages of the technology. Okay, so most of my focus today would be on the security risk. As I mentioned, right now, we basically have lots of changes in our existing system. We have old infrastructure, which we are trying to push them to be digitalized. We have lots of communication network in the system. We are adding two-way communication, basically connection between the customers and grid. And we are adding lots of different smart components to the system. So the system is expanding. It's basically in a distributed manner. We're expanding the system and we are adding lots of smart components to an old and fragile system. All of these changes result in a system which is very vulnerable to different type of cyber attack, because all of these pivot points in the system will basically result in a access point to a third party that can easily manipulate the system and basically take advantage of the system. If we ignore all these basically vulnerability in the system, we will end up having catastrophic events like the one that happened in 2007 in Idaho, Iran nuclear Stuxnet attack, or the attack that happened in the Ukraine in 2015, or Rochester utility attack in 2019. And actually this last Friday also we had another cyber attack in one of the major gas pipeline in the US. So it's something that we have to take serious. If I wanted to give you a general idea about the scale and basically cost of the cyber attack, we can see some example and number here, so you will get a general idea how important is the problem. If we wanted to look at the basically average price of a 0 day, which is the vulnerabilities that are there in the system, but the owner of the system is not aware of it. The average cost for each 0 day vulnerability is between 40,000 to 160,000 basically USD. And the average number of days that these 0 days vulnerability remains private, it means that the owner is not aware of it, is 151 days. Average number of days that it will take to patch these vulnerability means that the owner finds the vulnerability and then they have to do something to fix it. It's 120 days. average number of the malware that are basically released every day is 300,000. And the downtime, the average time for the downtime when the system is down and then you can recover everything is almost 200 days. So if you multiply all these numbers by each other, you will see each 0 day or each simple vulnerability in the system, it can cause lots of basically damages, lots of economic damages, and lots of costs for the basically operator or system owner. So it's really big risk. And if I wanted to look at it's a big cost actually. And if I wanted to look at the scale of the risk, I would say when it comes to the smart grid or other critical infrastructure, it's not like that we can deny the existence of this type of basically security threat, and we cannot at the same time be scared like the way that everything is announced in the news and you wanted to fix everything, you're really scared about it. It should be something in between. So you have to be aware of it. We have to think about having a specific solution for a smart grid and other critical infrastructure, but we have to do it in a realistic way. We should not panic. We should not forget about it. If I wanted to give you basically schematic view of how an attack can happen in the system, you can consider like a simple RTU control remote access that an attacker can take. This process generally starts when attacker will send an email, the hacker will send an email with the malware, and the email recipient can open the malware. Once the malware is opened in the system, the attacker can get access to the email recipient's PC. Once he or she get access, then they can send ARP scan, they can get access to the database, they can basically run some slave data SQL execution command, and then finally they can get access to the RTU remote terminal units, and then the system will be on their hand. So it's not something difficult, but at the same time, I will explain in my next slide that it's not something that can happen every day. So we have there are some techniques that basically we can take to prevent this type of attack. But before I explain more about those techniques, let's look at another basically real example, which was Ukraine attack, which was one of the basically major cyber attack that happened. It happened in this sector. This attack actually happened in 2015, as I said, in Ukraine. And in this specific attack, the hacker attacked 3 different electric utilities, and they resulted in power losses for 225,000 customers for several hours. And it was in the middle of the night and in the winter, which was really scary. What the attacker did was that they used a spear phishing email to gain access to the IT network. And once they were inside the system, they stole some credential using a different keylogger. And then they identified hosts and different devices, and then hijacked the distribution system. And they were able to basically systematically open or close different basically breaker in the system. They also got access to the industrial control system, which was basically the backbone of these utility centers, which manage and control the operation of the system. And then they disabled the power supply, they disabled the operational control system and everything else. You might be surprised if I tell you that this attack, basically the preparation for this attack happened 6 months before the date of the attack in December 2015. Because, and the reason for that is when it comes to the critical infrastructure, it's not easy to basically have such a coordinated attack, successful actually coordinated attack in a few hours or a few days. We are dealing with large-scale system, distributed system, and the attacker needs to stay in the system for a long period of time to collect information. In the case of the Ukraine attack, the attacker were in the system for 6 months. For 6 months, they were collecting information, they were taking advantages of zero-day vulnerability, they were collecting information about topology of the system, different devices in the system, location of the devices, and all these stuff. And after that 6 months, when they had enough information, they were able to basically run a successful cyber attack. And when you basically read the report, which was published after this attack, you will see that lots of, there were several operators actually that reported that there were some sort of suspicious activity in the system, like suspicious fault in the system, failure in the system. It's like that the operator would see a specific fault or failure in its screen, and then when they were sending the crew to fix it, there were nothing as an actual physical fault in the system. So there were some evidence which showed that attacker was launching different type of fault in the system, and then they were observing how operator would basically fix those faults, and based on those performance, they figure out the topology of the system, and they could find all pieces of the puzzle. So there were opportunity, if there were a mechanism there, to prevent this type of attack. But unfortunately, as I said, when it comes to the critical infrastructure, like a smart grid and other type of infrastructure, we don't have any active threat hunting or security mechanism that actively will look for this solution. All we have is IT security, basically, point of view. All we have is preventive action. Once the attacker bypass one of those walls, once they get access to the system, then there are no other mechanism to prevent basically the attack. So as I said, we already have lots of basically IT solutions. So still you might say, what's the main reason that we cannot basically take advantage of available IT security solution? Because there are lots of mature solutions, so it should be easy. If you look at the problem from an IT, basically a specialist perspective, you might say that a smart grid or other critical infrastructure are mainly working in an isolated environment. They don't have that many users, basically, so it should be very easy to secure them. We can use antivirus, firewall, customize a strong password, and we can patch devices regularly, and problem will be solved. So just think about these options that I mentioned here, and just tell to yourself how many of these options you think would work for the OT environment. So some of you might say only one of these options works, some of you might say all of them would work, but the answer is that unfortunately none of these options would work when it comes to the OT environment. And I'm going to talk about some of the reasons in the next slide. So as I told you, none of the basically mature IT security solution will work in the OT environment. I'm going to start with the first one, which is antivirus. The problem when it comes to the smart grid or industrial control system generally is that the vendors of the basically those infrastructure, usually they don't allow third-party scanning, and the condition is that if you use a third-party scanning, you will basically use the warranty of your device. So generally, antivirus will stop scanning the ICS pass folder because of this warranty problem. And if you basically put yourself in a shoe of the owner of a multi-million-dollar infrastructure, you will see that it's very difficult for you to jeopardize losing warranty just for scanning the system through the antivirus. The other thing is that when you basically use the antivirus, if you go through different folder, you will see that the antivirus is only able to basically scan the OT. Sorry, I see some background noise.
Can you please mute your microphone?
Okay.
Sorry, Doctor.
No, that's okay. So yeah, I was just saying that even if you use the antivirus, when you basically look at the basically folder path, you will see that the antivirus will only look at the IT property of the system. They don't basically scan the OT part of the system, like the OT operating system. So even if you use the antivirus, they're not going to scan the OT property of the system. So it's not going to solve the problem. You cannot get rid of all the threats and basically problems if you just regularly scan the system. The other basically things that is usually helpful when it comes to the IT security, but it's not working properly for the OT, is using a strong password. It does not help the OT basically environment, because unfortunately most of the time if you go to the environment, you'll see that the owner does not change the password, and even if they change the password, most of the time they don't use a strong password. The reason is that when it comes to the OT environment, there are lots of different people that are using that specific device or basically tools, and the owner does not want it to jeopardize the operation of the system by setting up a complex password so the operator might forget the password. So they usually avoid changing the password or changing it to something complicated. And I remember when I had a visit in one of these critical infrastructure, I noticed that one of the employee had basically a sticker on top of his computer, and it was obvious that it's a very difficult password that he wrote it on a sticker, so he would make sure that he won't forget it. But as you see, even revealing the password like this in front of everyone else, that's also another vulnerability. So it's like that setting up a strong password would cause lots of other problems when it comes to the environment, that lots of people are working with the device, and the operation of the device is highly important. We cannot stop the operation of the device actually. The other problem again, or the other solution that is usually handy when it comes to IT, but it's not useful for the OT, is the patching. What happens in the IT environment is that we regularly automatically patch everything, and we will make sure that everything is basically fixed if there is a problem. But when it comes to OT environment, most of the time the patching is impossible, because the owner of the device is different from the owner of the component. Like if you consider the Black Energy 3 attack which happened in the Ukraine, the attacker in that case, the attacker remotely updated the firmware of a Moxa import device, which was a serial to Ethernet connector, and it has a basically classical buffer flow vulnerability. But the vulnerability that the attacker used was not in the Moxa device itself. That belonged to another company named Electronics, which developed the code for the device. So you'll see there are lots of different components and pieces which are connected together, and you are working with one device, you're trying to patch one device, but the vulnerability belongs to another company. It's kind of hard to figure out who's even responsible for the patching. It's really difficult to figure that out, and because of that, everyone will put this problem in someone else's shoulder, and usually they forget about doing it. You also might say that why we don't do automatic patching. The reason is that, again, when it comes to the critical infrastructure like a smart grid utility center, we cannot risk sending an automated update on an environment which is heavily engineered and customized, because we don't know when we send an update or patch which component of the system might stop working, and that specific component might affect the performance of the whole system, which means regular patching might affect the operation of the system. And obviously we cannot tolerate shutting down an oil and gas basically facility or a utility center just for regular patching. So just imagine that if you wanted to do it weekly, even monthly, it's impossible. So it's not going to solve our problem. Generally, when it comes to OT environment compared to the IT environment, we have different priority. And that's also one of the main reasons that we cannot use the solution of these two sectors for each other. When it comes to the IT, basically security, confidentiality is the main basically criteria for us. We wanted to always make sure that we maintain the confidentiality. But when it comes to OT, availability is the first things. We don't want it to jeopardize the operation of the system. There is a high cost for that. So for all these reasons, we cannot just directly apply the existing solution for the IT domain and then basically have ready to go solution for the OT environment. There are generally several steps that we have to take to ensure the security of these environment, smart grid, and other critical infrastructure. What we can do in short term is that we can add different incentives for the vendor to improve the reliability and security of their basically product and to be responsible for patching, let's say. But it's not basically enough. And in a medium term, we need to develop secure and customized solution for these environments. For that, what we do in my research is that we try to take advantages of AI, and we wanted to develop different security solution, decision support system. Unfortunately, when it comes to the OT environment, we don't have any decision support system for the control center. When you go to control center of the even major basically utility center, you will see that all decision will be made at the time of the basically crisis by a group of human operator. You don't have any decision support system to at least suggest them what is the best action to take. And obviously, in a longer term, we have to basically develop different resilient control algorithm, resilient and intelligent control algorithm to be able to control the operation of the system. And most importantly, we have to make sure that we will consider security in the design level. Right now, all we have is that we are using devices which were not designed with security in mind, and we are connecting them to internet. We are basically forcing them to interact with each other. So that will raise lots of problems. It will take a long time to basically renew all these infrastructure and facility because it's expensive. And again, renewing them means interruption in the service and all this stuff. So for a long period of time, we might need to develop solutions that work in the existing environment. And at the same time, we have to think about designing solutions that basically designing devices with security in mind. As I said, what we do in my research is that we generally try to take advantages of artificial intelligence, AI, or let's say machine learning and deep learning, which are subset of AI, because AI is somehow an abstract idea by itself for now. So what we do most of the time is taking advantages of machine learning and deep learning. And as you all know, basically AI already proven to be basically useful and powerful technology, and can be used in different aspects, in different basically solving different problems. And cybersecurity is also one of the problems that AI can be useful. So why we are interested in the AI, or why everyone is shifted toward using AI right now, is because we have to deal with huge amount of data. As I said, one of the attributes of the smart grid is that we have an information-based system. We have lots of sensory devices in different locations of the system. So we have to basically process these huge amount of data, and we have to basically extract useful information out of them. And when it's basically the problem, AI is really useful in basically extracting information from the huge amount of data. And as I said, it's already used in lots of different domains, and in all of these domains, it showed that it can basically improve the performance. If I wanted to look more in-depth look why we're using machine learning and deep learning for specifically for a smart grid, I would say that most of the traditional smart grid basically analysis and control and decision making are primarily based on physical modeling and numerical calculation actually. So because right now we are dealing with a lot more complicated and complex system, and we have lots of uncertainty involved in the smart grid, and those uncertainty is because of the using renewable energy sources, different type of solar cell, wind power, and all other type of renewable energy sources. All this complexity and uncertainty make the modeling non-practical or inaccurate. So although we cannot totally replace model-based techniques, we need data-driven techniques to come and help for those areas that the complexity is high and we cannot just model everything mathematically. Besides that, we need to have full observability, and we have to be able to control the system as soon as possible to avoid the cascading failure and different type of fault in the system. And for that, we need lots of predictive analysis. Again, when we wanted to do predictive analysis, AI is a tool that can really help us. I also already talked about the huge amount of data, which is another reason that we wanted to use AI. If I wanted to specifically talk about the use case of AI or machine learning, let's say in cybersecurity, I would say it can be used in triaging to basically augment the rule-based detection system, which basically save lots of time for us. And it can be used for threat hunting, which means that we have to actively and dynamically search through the data for recurrent pattern, anomalous behavior, and other type of outlier. And the other basically cybersecurity problem that AI can help is in incident analysis. When an incident happened in an event of the attack, AI will increasingly answer the questions like what happened in the asset, which asset is under attack, or what are the sequence of the attack, and all these type of basically questions. And it also can be used for incident response to basically create a playbook for us that we can give it to an operator and then can make an informative decision as soon as possible. In my research, we are generally focused on developing a basically reliable AI-enabled tool for analyzing and detecting OT threat in different critical infrastructure. So we are mainly focused in active threat hunting, detection, cyber threat intelligence, generally for different critical infrastructure, including a smart grid. And we also are focused on developing different intelligent monitoring and control solutions to be able to basically control the performance of this system or maintain the resiliency of the system in case of attack. So in the next few slides, I'm going to give you a couple of examples of different basically framework and model that we proposed, which shows promising results. Here, this is one of our work that we proposed an unsupervised basically attack detection method to extract the patterns of changes in false data injection attack. And that's one of the basically most famous type of attack that regularly happens in the smart grid. For this work, we first decomposed our system into several subsystems because we wanted to basically reduce the size of each substation. And then we used symbolic dynamic filtering to build a computationally efficient feature extraction to discover the causal interaction between different subsystems. We basically used the time series data. We converted the time series data into symbol sequence, and then we used dynamic Bayesian network from this sequence to basically compress the information into a low-dimensional statistical pattern. Generally, our assumption here was that cyber attack will change the interaction between subsystems, and it will result in different patterns. So we employed the restricted Boltzmann machine to identify cyber attack based on the probability and energy level of the event. Generally, RBM amounts to maximize the likelihood of the training data with low energy state. So an anomaly or attack can appear as a configuration with low probability or high energy. We basically tested this model for several different like detection threshold, attack sparsity, attack magnitude, and in all of them, it could basically, with high accuracy, it could detect the possibility of the false data injection attack in the system. In another work to further improve our model for larger and more complex system, we decided to use representation learning to reduce the dimensionality of our data and basically to reduce the computational burden actually. Our goal in this specific work was to develop a two-level ensemble deep learning attack detection model for a smart grid. we had two phases in our model, the representation learning and the ensemble model. In the first phase, we had two stacked autoencoder model, which was used to extract new representation out of the raw feature for basically each class of our data. And then we used those new representation on different classifier on physical layer data for the smart grid. And in our data set, we had real data set, simulated data set for smart grid, oil and gas, water resources, and different critical infrastructure. Overall, when we use this new basically representation learning model, new sort of data, we noticed that the performance of all base classifier will be improved by 20 to 40% when we use our representation learning model, which was very promising. And it had obviously less computational burden. In the next step, to develop a threat hunting and threat attribution model, which is very important for the critical infrastructure, basically security or OT security. For the first time, we actually proposed a threat hunting and attribution model using our previous representation learning model. What we used here was that we basically used the previous new representation data or the architecture that we proposed for the new representation of the data. And then we used a super vector of this new representation. We passed them through principal component analysis to select a subset of feature with higher importance to further basically reduce the size of the problem. And then we fed them to first to a decision tree classifier to detect basically normal and abnormal condition. And once we had basically a normal and abnormal condition, then we used ensemble of one class classifier for threat hunting. We use one class classifier because with this type of classifier, you can basically classify each attack with a high accuracy, because those classifiers are trained on a specific type of attack, so they can detect it with a very high accuracy. So the hypothesis behind our threat hunting model was to detect cyber attacks which were not detected yet. So we had one detection model, but as I said, not all attacks are basically well known. We have lots of unknown attacks in the system which appear as different basically anomaly in our system. For those anomalies which happens all the time, we developed the threat hunting model. And for our threat hunting model, we used a multi-view approach when we fed different view of the system. Like if I wanted to talk about malware, like opcode, bytecode, library code, different view of the system. When you fed different view of the system, that increased basically the accuracy and efficiency of the model a lot. Because for an attack, from attacker perspective, it's very difficult to change all view of the system at the same time. So a multi-view approach generally would work a lot better compared to a single view approach. For this work, we used both IT and OT feature like IP data set, network data set, network flow data, physical data like MAC address, device ID, system log, Windows event, and everything. And as I said, we proposed the model as a multi-view model to consider all these together. And you can see in the next slide that we basically managed to have a higher accuracy compared to other proposed method in the literature. As you see, the blue one is ours. And we were able to basically attribute the attack to each family that it's belonged to with a very high accuracy. Here in the confusion matrix, you can see it. Attack attribution is very important because when you have an attack, the way that you make decision about the attack, how to fix it, how to take other basically action, totally depends on the family of the attack, how the attack will propagate in the system and all this stuff. So it's not enough just to detect and say that there is an attack in the system. It matters to know what type of attack, to what family the attack belongs to actually. I have also another example here for our work, which was basically an improved version of the multi-view model that we basically developed. And here we also added a multi-layer data set. So aside from the IT layer data, we had also physical layer data. Aside from the cyber layer data, we also added the physical layer data at the same time. For this specific basically framework, we had all attack detection, attack prediction, threat hunting, and threat intelligence model all at once for a smart grid environment. This system was basically generally designed to help the security expert to first of all detect the attack in the network and as well as in the node basically level. So it has, as I said, it has 3 components, and all these 3 components are interacting with each other. For all of these components, we are using Ensemble's model, different customized deep model, which are specifically designed for the OT environment. And that's basically the very first theme solution that we are proposing for OT environment, which can work in the smart grid environment as well. This is actually an industry project. I cannot give too much information about it, but so far it's showed us very, very promising results, and we're really interested in commercializing it. So this was only some example of what we did in my basically group. We have lots of other work which is focused on the basically fault prediction, fault analysis, developing different basically control action, and working with different IoT basically level data. But for the sake of the time, I couldn't include all of them here. You can basically see them on the list of paper that we published. So I talked about the advantages of the AI and how useful it is for the cybersecurity analysis. But obviously, there are some challenges when we wanted to use AI for this specific purpose. One of the basically problem is related to the data sample. Because still, although I said that we have lots of basically data which are generated through the system, but still when you compare it to other environments, data sample are limited. We need a lot more data to have, to be able to have full observability of these environments and to basically develop a highly functional and efficient AI model. The other basically problem is that still the reliability of AI basically model that we are developing and we wanted to apply to the power systems or other critical infrastructure, it has lots of questions behind it, and it still needs improvement. So far, we can only use these AI tools as an auxiliary tools to come and help the operator. We cannot basically replace the human resources, and it's far from basically what we are right now. Aside from that, we also need lots of improvement in our infrastructure. As I said, we have lots of old infrastructure, and in those old infrastructure, we are not even able to have a smart, basically sensory devices. We are not able to have full observability of those infrastructures. So we need to improve those infrastructure as well. And also, we don't have enough basically industry-specific algorithm, which is basically basics of the AI, compared with the basically perception, prediction, and security maintenance. Algorithm adaptability of AI in power systems is still weak, and it's one of the key points which we need to have lots of follow-up researchers to basically improve the basic algorithm and propose a special intelligent algorithm for power system specific for this industry. There are also privacy issues that we have to make sure that when we are using AI, we're not basically jeopardizing and violating privacy of different users. And obviously, AI is controversial, and it's not like always is a useful technology. Most of these challenges are basically obvious, but I'm going to talk about the last two in my next two slides. One of them is, as I said, one of the challenges is related to the privacy. When we're using data for our analysis, as I said, we have to be careful not to violate the privacy. So we have to make sure that research will move forward at the same time in both directions. because most of the time people confuse privacy and security together. Privacy is basically the ability to prevent unwanted transfer of information when a legitimate transfer happens, actually. So when it comes to the privacy, encryption is not a solution. You cannot encrypt the data and say that privacy is preserved. We need to transfer the data as well. But with the security problem by definition is basically protocol and primitives that clearly distinguish a malicious adversary versus an intended use and a secret versus non-secret basically type of data. So it's a different problem. To basically maintain the security, sometimes the encryption of the data might basically helps us. So these are two different things. If I wanted to give you an example, I would say that smart metering devices that we are using is an example of implementation of the smart technology that we need to use AI for that, with that, but it might also affect the privacy of the people. Why I'm saying that? Because when you have these smart meters in different locations, like let's say in your home, that basically those data usage can threat against the customer privacy, because with those data usage consumption, it's easy to deduct the pattern of home activity. And that's basically lifestyle of the people. And unfortunately, we don't know who owns the data, who controls the data. It's still a question. Is the customer owner of the data? Is the utility center owner of the data? Is the government owner of the data? We don't know who is owner of the data and who we have to basically go to if we have a problem with the usage of those data. Besides that, these data can be used to offer us personalized service. At first, you might think that it's very good. Why we have to be offended if someone wanted to offer us personalized service? But if you look at it deeper, you will see it's somehow against our privacy, because usually business owners, they use these data to manipulate people to think differently, to think they need something that we might not need at all. So that's also in another way, basically violating people's privacy. Not everyone likes to be pushed to think differently. So the data can be misused also in that way to affect people's privacy. Obviously, what I'm trying to say here is not that we have to avoid using all this technology because it has privacy concern. What I'm trying to say is that we have to be careful and we have to implement different type of solution to basically maintain the privacy of these smart meters devices are basically preserved. We have to do some sort of utility privacy trade-off when we are doing design in these devices. We have to basically develop different privacy invasion detection or prevention techniques, and we have to use different type of data masking, data anonymization, and all these different techniques to make sure that while we are using these data, we are not violating people's privacy. And finally, AI is controversial. So lots of people already raised concern about the future of our basically world with AI. It can be basically, it can easily beat us in near future if we don't basically think about it carefully. As an example, you can consider the Thai bot. Thai was an artificial intelligence chatterbot that was originally released by Microsoft on March 2016, and it was deleted only after 16 hours. The reason was that it caused subsequent controversy when it began to post rude and offensive tweets in Twitter account after it chatted with several basically different people and users. So people who designed this basically chatbot, they forgot that it's not able to distinguish between good and bad source of data. Whatever you feed the basically AI model, it will learn based on it. And that's something we have to be very careful about it, because otherwise we will end up having an engine that is not working based on what we want at all. Another example is basically the paperclip, famous paperclip example. There's a well-known thought experiment in the world of AI that poses a simple but potentially very scary question. The question is, what if we ask a super intelligence AI to make tons of paperclips? Different people already provided different answers to this question. But one of the best basically answer, which was provided by an Oxford philosopher, Nick Bostrom, if I'm not wrong, was that he said the answer all depends on how we train the AI. If we give it a common sense, it might ask us how many paperclip do you want? If it doesn't know to ask, it might just make paperclip forever. If it's a super basically intelligence AI that we accidentally forget to put any human ethics or value in it, it might decide that the most efficient and profitable way to make paperclip is to wipe out humanity and terraform the planet into one gigantic paperclip factory. So when you think about this, you will see that it could be really scary if we don't consider all aspects and just jump to the technology. We have to make sure that we will consider all different aspects of the problem and we move forward our research in all of these aspects at the same time. So ethics of AI is not the focus of my research, but I always try to consult with other people who are working in this domain to see what might happen with our technology if we don't consider all these facts. Like one simple example which might be close to here is adversarial type of attack. When you develop AI engine, you also have to be careful that there are adversarial examples that might affect the performance of the system and manipulate your AI system. So you have to consider all of these basically techniques. And as I said, any powerful technology can be misused, and AI is not as an exception. So although it's a good technology, it has lots of advantages, we have to be careful how we are using it. So that was the my last slide, and here is a list of the references that I used. And finally, I would like to thank everyone for their time, and I would like to mention that we're always looking for collaborations in our group, and with collaborators in different universities, student, postdoc, who are interested basically in machine learning, game theory, intelligent pattern analysis, generally for OT, IoT environment, smart grid, and other critical infrastructure. So thank you very much for your time, and I'm open for questions.
Thank you, Dr. Karmipur, for your presentation. It was really interesting and very informative. Too much information over there. And yeah, we have a couple of questions from the participants here. One of the participants is asking, what is the hardest challenge for AI? I'm not sure what he really perhaps means by that, but yeah.
Honestly, it's kind of hard to say what is the hardest challenge for AI. As I said, it depends on the domain that you're working with. Different domain might face with different challenges. If I wanted to talk about specifically with the smart grid analysis, as I had in one of my slides, most of the problem that we have right now is lack of enough data. When we wanted to develop different solutions, specifically when we wanted to develop different solutions with multi-layer data, unfortunately, it's really difficult to find the data that record all these events at the same time. When you go to different utility centers, even if you wanted to talk about security of the utility center OT, they always refer you to the IT department. It's like that all the data that they will collect about the security analysis is in the IT layer. It's kind of hard to basically find OT layer data. So I would say one of the major challenges would be have a reliable, non-biased data sets, which is basically fuel for the AI.
Thank you. And we have a couple of more questions there. They are asking that as known, cyber attacks are unpredictable and can be unseen or unexperienced. So unexperienced threats. Without training data, how power grid can be protected for the unseen, intruders? Yeah. How power grid can be So yeah, just
Then when we talk about the unseen type of data, obviously attack detection will not work, because detection is for those type of attack which is already known. We know what's the type of the attack and we develop a solution, we can detect them. When it comes to the unknown attack, we mainly go toward anomaly detection techniques. In security community, we call it cyber threat hunting. In cyber threat hunting, what we do is that we dynamically look for abnormality in the system. So anything that is abnormality can goes to the category of the basically cyber attack. And then once we found the abnormality, we will check different nodes in the system. We will check different data that we have from the threat intelligence sector or other component of the system. And then we can figure out if it's an actual attack or maybe some other type of anomaly.
Okay,
so
thank
threat
you.
hunting is the approach that we have to take.
And you're saying that can we solve the same security solution to each utility operator that have different topologies and characteristics?
Obviously, we cannot have one single basically algorithm that can fix the problem in all utility center. But the idea behind it, the backbone of the system would be the same. But when we take it to a new environment, we always need to customize it, because different environments are coming with different basically requirements, with different topology, with different architecture, and all of those factors should be considered when we are modeling the system. So I would say if you develop something which works in one specific substation, you can say for sure it will work for the smart grid environment for utility center, but you cannot just plug it in a new system and expect it to run a good result. We need training, we need customization. After training and customization, it would work.
Thank you. And you're saying that does AI simultaneously detect the type of attack and prevent it?
You cannot say I have one single AI model that can do it, but you need a couple of different AI model and components. And yes, when you have different components, you can have one component for detection, one component for the prediction, one component for projection, one component for cascading failure analysis, but you need different components, because it's like you might need different type of information to be fed to the system. The architecture of the model might need to be different. So we don't need to have one single unified model. We can have different components in our system to do all these tasks.
Thank you, Dr. Karimpour. And you're asking about, do you have any selection, like which hardware or setup infrastructure do you utilize to embed an ANN or DNN for your research?
I don't know what exactly they mean by this question, but if the question is for simulating the data, what we basically use is that we use some real-time simulator which are developed by OpenRT and RTDS. They have real-time simulator which basically simulate a smart grid environment. They have emulator. They have HyperSim basically environment, and all of these together can basically model a small scale, a smart grid. You can launch a cyber attack. You can see how the attack propagates in the system. And if you wanted to model the communication network, you can use Omnet++, for example, to model that communication network area. Some setup like this would be good to generate the data if the question is about how we generate the data for different scenario.
Okay, thank you so much. There are many people also thanking you for the presentation. I'm not reading them one by one, but they are appreciating the presentation.
Thank you very much for listening.
Are there any efforts to develop specific neural network architectures or algorithms that are specific to the smart grid area?
The question was, is there any effort?
Yeah. Are there any efforts to develop a specific neural network architecture or algorithms for the smart grids?
I cannot say, if you mean fundamentally changing the architecture of the neural network, I didn't see any specific basically research to theoretically wanted to change the architecture of the neural network. What we do is that we try to modify the architecture to basically feed the data and change the architecture in a way that is the best one, like by different feature extraction analysis, by different feature weighting, by different ensemble model, representation learning. We're trying to put all these components together to be able to work in this environment. But we don't necessarily need to change the architecture of a theory of the neural network or deep model. We mainly work with the deep neural network, not the neural network itself, because we have a deep model can process huge amount of data better compared to the neural network. So most of the techniques are based on the deep model, specifically for threat hunting.
Thank you very much. And they are saying, can we consider the cyber attack behavior or their damages as physical faults and design fault tolerant controllers to accommodate the attack?
Cyber attack.
Sorry, to accommodate the effects of the cyber attack.
Cyber attacks are different from fault. So even when we detect a fault and cyber attack, we make sure that in our engine we can distinguish between the fault and cyber attack. However, a cyber attack can result in a fault in the system. So most of the time what happens is that when a fault happens due to the cyber attack, specifically it's a basically cascading type of event. It's happening in several different basically subsystems. It's more a fault. You will lose the access to different components of the system. But obviously, if we have some basically devices that automatically can clear the fault in a matter of seconds, or can predict if the fault can make the system basically unstable or not, obviously it will help us to mitigate the effect of cyber attack. But we cannot prevent cyber attack or resolve all the problem by this type of component design. But it definitely helps for the basically consequence of the attack.
And there is one more question. They are saying that these models need huge amount of data. What about the data storage components? And also, can we analyze these data in real time?
We don't have right now, at least we don't have problem with the data storage. Actually, like maybe 10 years ago, that was a problem. And that was like we didn't use AI into this extent that we are using right now. Right now, we don't have that much of basically a storage problem. But obviously, whenever you have huge amount of data, the algorithm would be slower. So still, although we don't have problem with the storage, we always try to make sure that we only use the right amount of data by feature extraction, feature analysis. We wanted to get rid of the extra data. And it's hard to say that we can make it real time, because to claim that it's exactly real time, it's really difficult to claim. Hopefully in the near future, we can have algorithm that will be trained in the near time and can be updated in the near time. But right now, what we do is that we wanted to do as much as possible predictive analysis. Because when you do prediction, even for example, when you wanted to design a controller, if you do predictive analysis, you can decide when the load shedding or other basically tasks are required. So that way you can save time, and then your controller would work in a real-time manner. So it's hard to say that the algorithm can be trained in the real time very accurate. It can be customized, I would say. So we need to have a base for it, and then we can customize it in a real time, let's say.
Thank you very much, Professor Kantarci. I think that was the end of the questions that we had here for this session.
Thank you very much for your time.
It was really a great presentation, too much information over there.
Thanks.
So we will check the recordings again, and of course we will double check with our speakers again about the recordings and what we have, and then we will decide on the next steps. And about the presentations and the slides, also we may check with the speakers if there are any possibilities.
So once again, I would like to appreciate Dr. Kantarci and Dr. Karimipur for informative presentation. It was a great pleasure to have you in this event, and hopefully we're going to continue working with you in future. So we have many tracks of women in engineering in coming months. So we are going to schedule a couple of events, and hopefully we will reach you out again to be in touch with you to further events. So it was a great pleasure. Hopefully everybody will get vaccination, and we will meet in person one day in a conference or someplace better than this, hopefully.
Yeah, we hope to. Thank you very much for organizing the event.
Thank you. Have a good day and take care.
Yeah, have a good day.
Thank you very much, everyone. Have a good day.
Thank you. Have a great time. Bye.